Okay, welcome to Scaling Machine Learning with Python and Dask. My name is James Lamb. I'm an engineer and data scientist from Chicago. I am a maintainer on the LightGBM project, and I've been involved in the Dask ecosystem for the last few months, getting close to a year at this point. I'm really excited to be here at ODSC talking with you today about machine learning using Python and Dask. So let's get right into it. Before we go any farther, I just want to offer as a disclaimer that I am an engineer at a company called Saturn Cloud, where I work on a managed data science platform that does include a managed Dask component. This talk is not about that. This is the last time that you'll hear me mention it, but I do want you to know that I work on problems in and around Dask and machine learning in Python professionally. Okay, so to begin, let's talk about why you might choose Dask and the Dask ecosystem for machine learning workflows. So many of you in the ODSC audience should recognize some of these packages. These logos should look familiar to you. Data scientists love Python, and there are many great reasons for this. One is there's this very rich ecosystem of available packages. Scikit-learn, stats models, Plotly, Pandas. These are very, very powerful packages, very powerful open source projects with a lot of maintenance effort, a large online presence of Stack Overflow questions and documentation. And there's a reason that data scientists love these libraries. I love these libraries. If you said that you didn't love any of these libraries, I would really question, what you've been doing data science in. However, I'm sure you knew there was a but coming there. However, many of the popular data science libraries were designed for use on a single machine. And so they put a lot of energy into the API, into the way that those libraries interact with other libraries. But the focus all along was single machine computing. And so what that means is when you get to a point where you have maybe big data or a bigger idea and you like using these libraries, you may find that you're struggling to figure out kind of how to make those two things work together. Before I go any further, I want to explain what I mean by big data and big idea. I'm sure you've heard the phrase big data before. I'm not going to give you like the 3 V's or 6 V's of big data or whatever the clickbait definition is. But what I want to explain here is in machine learning workflows, you can have big data, meaning that you have a lot of features. You can have big data in the form of many observations, but you can also just have big problems. So you could be working with a data set that you might describe as moderate or even small sized, but want to train a very large model. Or maybe you want to train many models during something like hyperparameter tuning, and you want to be able to do that in a reasonable amount of time. So as I go through this talk and I talk about Dask and I talk about distributed computing, I want you to resist the urge to say, my problems are small, my data sets are small, I don't need to think about Dask and Ray and Spark. I want to kind of pitch to you that you may be limiting yourself by staying on a single machine. I also want to remind you that the data science libraries in Python can be very memory hungry. This quote is a little bit dated at this point, but I still think it is a generally useful reference point. A few years ago, Wes McKinney, the creator of Pandas, wrote this blog post and gave this conference talk. I actually saw a version of this talk at ODSC West, where he talked about the 10 things he hates about Pandas. And in that talk, he mentioned that his rule of thumb for working with Pandas is that given a certain data set size on disk, you should expect to have about 5 to 10 times as much memory as that size on disk to work with that data in Pandas and to kind of do all the interesting Pandas stuff that you do with data. So for those of you who are thinking, I don't need distributed computing, I don't need out-of-core computing, any of this stuff, my data sets are small, I would again recommend that you consider that it doesn't take too much to exceed the physical resources of the kind of standard data science workstation. Okay, so when you're doing machine learning work specifically, and that work, You design an approach to a problem. You say, I'm going to use this algorithm, this data set, like here we go. And it looks like your initial design requires more physical resources than you have available to you. You kind of have three basic options to continue moving forward and come out of it with a model that you feel good about. The first option is to use less data. And so what you might do is to take your entire data set and to put it into a place that can store a data set that large, and then execute queries that sample or downsample or otherwise aggregate that data. And so, for example, if your data are in files, you might store them in an object store and then query them with a kind of query over files type of tool like Apache Drill or Athena or Presto, something like that. If your data kind of work well with a relational database type of system, you might put them into a traditional relational database management system like Postgres, MySQL, Microsoft SQL Server, something like that. Or you even may use one of these newer data warehouses, cloud-based data warehouses, and those are tools like Snowflake, BigQuery, Redshift, things like that. And so in that case, you'll put all your data there. You'll have tons and tons of data in the place where you keep your data, kind of your system of record. And then you'll write queries that define a smaller subset of the data that you still think is kind of okay to work with for machine learning purposes. That's one option. Another option that you have is just to go get a bigger machine. So your machine's not big enough, go get a bigger machine, right? There are several reliable public cloud providers. You can pretty easily go spin up a machine from Amazon, from Microsoft Azure, from GCP, and a host of other providers. But this is going to cost some money. And I know this seems kind of like a trivial statement. Like, of course, if I go buy stuff from AWS, it's going to cost money, right? But I want to explain a little bit more what I mean when I say that the just get a bigger machine option is going to cost money. When you provision a single virtual machine from one of these cloud providers, this is called vertically scaling, basically. You just say, I'm going to take my one thing and run one bigger thing. You're paying for the time that you're reserving that capacity, regardless of how efficiently you use that capacity. And so what that means is you're going to have to provision that one large machine to have, for example, enough memory for the peak memory usage of your entire training pipeline, or your entire grid search pipeline, or kind of whatever you're doing with machine learning, right? And what that means is that for much of the time that you're working there, when you're doing work that isn't fully taking advantage of that memory, say like in the setup stage where you are maybe doing a bunch of data loading, or maybe in a post-processing stage where you've kind of freed a lot of the data from memory, but now you're making plots or you're calculating metrics or things like this, you're going to be paying for the time on that larger machine while not actually using those resources. So this is one of the ways that the just get a bigger machine plan, though it always sounds good, can actually cost you more money than maybe you needed to spend to solve the problem. And then your final option is to use more machines. And so there are very specific distributed training options available to you from several machine learning frameworks. XGBoost, LightGBM, TensorFlow, PyTorch, they all have their own kind of built-in opinionated way to do multi-machine versions of the things that you're used to doing in those libraries on a laptop. And then there are also more kind of general purpose distributed computing tools. For example, Apache Spark, Ray, and Dask. And so this is kind of the lay of the land. These are kind of your three options as I would describe them when your machine learning work requires more memory, more CPU than you have available. As I mentioned, some machine learning frameworks have built-in distribution, built-in kind of multi-machine versions of themselves that you can use directly. These are great in limited settings. So if all of your training data are ready to go, it's just like a bunch of Parquet files in an object store like S3 or something, and you just want to rip through doing a bunch of distributed training on them or something like that, like maybe with XGBoost or LightGBM, these options might be great for you. However, the thing that is parallelized over multiple machines in these frameworks, especially in the case of the gradient boosting libraries, tends to be the training process and maybe the evaluation process. But if you need to do highly custom feature engineering or data loading, if you need to, for example, load batches of data not from an object store, but out of a database by executing a query and using custom credentials, if you need to do substantial feature engineering, maybe you need to join together sort of your main observational data with other data, think about like merging a bunch of transactions with some customer segmentation data or something like that, right? These frameworks by themselves are not really going to give you a lot of power to be able to do that. You might find that they're a little bit limiting in that sense because they weren't designed to be kind of general purpose, data extraction and data transformation tools, right? They're designed to be machine learning libraries. And that's why frameworks like Apache Spark have been so popular since they were introduced. And shortly before Apache Spark, the whole Hadoop ecosystem that kind of offers the same thing, that offers general purpose multi-machine computation. That's like the kind of highest level single bullet point way to describe this thing that we're talking about. This is not a talk where I'm going to try to convince you to use Dask or Ray instead of Apache Spark. Apache Spark is awesome. Apache Spark has a huge community of contributors, of people writing documentation and tutorials, of companies that offer support for it. Apache Spark is widely used for a reason. It's extremely powerful and it does a lot of cool stuff. What I want to kind of talk to in the next couple minutes, the next couple slides, is basically how Dask works, and I want to explain how Dask works by comparing it to Apache Spark. And then later in the talk, we'll go much more into detail on how Dask works. And so first I want to start by saying that, Dask and Spark are very similar in a lot of ways, and in two particular ways that are really important to machine learning workflows. So both Dask and Spark offer options for doing distributed training. I should stop here and clarify something else about this talk. You're going to hear me use the word distributed a lot. When I say distributed, what I mean is multi-machine training. So multiple physical machines are all cooperating in the process of training a single model. You may hear other tutorials or other talks use the word parallel or parallelized and distributed interchangeably, but you're not going to hear me say that. When I say something is parallelized in this talk, I'm going to mean that it is using maybe multiple CPU cores on the same machine. So distributed, I'm talking about multiple machines all collaborating to help you with some task. Okay, so distributed training. Distributed training means maybe my data is physically partitioned into multiple machines, and I want to run a training process on each of those machines that is not going to be, each process training its own individual model, but kind of each process contributing to the overall final model that I get. Both Dask and Spark have options for this. In Spark, you can use SparkML, SparkMMLib. There's a project from Microsoft called MML Spark that implements a number of popular machine learning algorithms, including LightGBM for Spark. There's an XGBoost for JSpark that lets you run XGBoost models on Spark. And in Dask, there's a similar ecosystem. There is a project in Dask called DaskML, which tries to mirror the API of scikit-learn as close as possible. XGBoost and LightGBM have built-in native Dask integrations. There's TS-Fresh if you're working on time series problems. So both of these frameworks have distributed machine learning training options. Both frameworks also offer distributed data structure support. So in Spark, kind of the most famous Spark data structure is the RDD. That stands for Resilient Distributed Datasets. But there are others in Spark that look and feel a little bit more like the data structures that data scientists like to work in. And that's like the distributed matrix or the data frame. In Dask, you have the exact same thing. There are these data structures in Dask called Dask collections. There's a Dask array that looks and feels similar to a NumPy array, a Dask data frame that looks and feels similar to pandas, and an object called Dask bag, which is sort of an arbitrary ordered collection of whatever, somewhat similar to an RDD in Spark. So both of these tools, they're going to give you the ability to use kind of distributed tabular data structures and to feed those into distributed machine learning training frameworks or libraries, which is awesome. But let's talk about some of the ways that they're different. And so first I want to talk about some of the advantages of using Dask over using Spark. I shouldn't even say advantages. Some of the reasons that you might prefer Dask for your particular type of work to Spark. And the first big one, the one that really kind of sold me on Dask, is that Dask is a Python first project. All of the code written in Dask is Python all the way down. I mean, there is some C with Python, just like there is in every Python thing that you look at, right? If you go far enough into Python, you're gonna find some C code. You're gonna probably find some Fortran code. But what I mean here is all of the kind of user-facing code in Dask is all written in Python, and the core internals, kind of the orchestration layer, is all Python. And so what that means is you don't have to deal with this situation that you find using PySpark, where you write a pipeline, you're feeling good about it, you deploy it out to the cluster, and then you're staring down the barrel of a 200-line Scala stack trace that you don't understand because you only know Python. That's not going to happen in Dask. Dask is Python basically all the way down. The next kind of big benefit of Dask over Spark is that the Dask ecosystem has put a lot of energy into and emphasis on API parity with some of the libraries that I mentioned a few slides ago that you know and love. So a Dask data frame, this is a distributed data frame where the different pieces of the data frame are broken into chunks, maybe on different machines. The code that you write to manipulate a Dask data frame tries to follow the Pandas API as closely as possible. You're going to see later in the demo portion of this talk that I'll be evaluating a machine learning model using the metrics functions from Dask ML. That project's code tries to emulate the API of scikit-learn as close as possible. And so what that means is when you take kind of code that works on your laptop, code that works on one machine, and you decide to go run it on Dask, you don't feel like you're writing Dask code. I can't tell you that it's going to be as easy as import dask.dataframe as PD and just all the rest of your code that was pandas will just work. It's not quite that easy. But very, very, very very, very much less friction in converting a local code base into something that will run on Dask than converting that same code base into something that will work well with Spark, at least in my experience so far. So this is another big selling point of Dask and why you might consider it if you're working in Python. Next, Dask gives you finer grained control over the task graph than Spark. So both Dask and Spark, you express a workflow to them, and they translate that workflow into an ordered graph, and then rely on some internal details that will execute kind of the tasks in that graph and handle dependencies between different tasks, sharing data, stuff like that. In Dask, you can build up your task graphs from scratch if you want. You can really customize as much as you want and still get some nice parallelization and kind of management and orchestration benefits from Dask. In Spark, that isn't necessarily true. And I also would say, to be fair to Spark, that isn't necessarily a design goal of Spark, right? So in Spark, kind of the patterns that you're going to have the best time with are based on those functional programming primitives like map, reduce, filter, group by, things like that. And you may find that it's a little bit difficult to implement kind of processing pipelines that don't fit neatly into that paradigm. But when your processing pipelines do fit neatly into that paradigm, you will probably find that Spark is a really nice experience, and you can generate a Spark program that does what you want pretty quickly. So it just kind of depends. But if you are designing something kind of highly custom from scratch, you may consider that the higher level of control over the task graph in Dask is kind of a benefit of Dask over Spark. And then finally, Dask has built-in kind of native support for multi-dimensional arrays, which can be difficult to work with in Spark. Okay. However, there are also some reasons that you might prefer Apache Spark to Dask for machine learning and kind of data work. The biggest one is the presence of a mature, well-documented, feature-rich SQL engine. So in Spark, you can use a component of Spark called Spark SQL that will allow you to basically generate data frames by writing SQL over collections of files in a distributed file system, or over kind of data that's already sitting in distributed memory, all kinds of different inputs. This is something that Dask is lacking. So there are projects in the Dask ecosystem like Blazing SQL, like Fugue, like Dask SQL, which are trying to offer this for the tabular Dask collections like the Dask data frame. Those projects have been very exciting to watch. It's been interesting to watch their development. They are not close to the level of maturity of Spark SQL yet. So for now, if you are just kind of like crunching through a lot of SQL queries over very large data sets, Spark might be a more fun time for you. Next, Spark has some high-level optimizations that Dask does not offer, and in some cases, can't be expected to offer. So I mentioned a moment ago that Spark puts some more guardrails on the way that you write programs and the way that you describe processing pipelines, right? So you use these functional programming primitives, and there's kind of these like very well-defined ways to express a workflow in Spark. What that means is, because there is a higher degree of constraint on the way that you write your code, Spark is able to look at kind of the execution plan, at the graph that describes your workflow, and it's able to automatically add on some optimizations before executing. So kind of the trivial example, right, is if you have a pipeline that is like loading some data, adding some columns, changing some other stuff, and then maybe like step 7 or 10 or 15 is a filter by key, where the key is actually a column that's present in the initial data frames. Spark might be able to look at that and say, wow, all the way down here, we're going to filter out any records that don't match this specific value. I bet I could just pull that filter all the way back to the top of the pipeline and then not even load that data, not spend the time loading it, not spend the memory storing it, not spend the processing, effort processing it. Could be cool. So that's kind of like a very hand-wavy description of the optimizations that I'm talking about, but those things are more possible for Apache Spark to do than for Dask to do. Now, when Dask looks at your task graph and before it executes it, Dask will do some automatic optimization. I'm not telling you that there's none, but because Dask offers you finer grain control, the trade-off there is that there's less that Dask can kind of automatically optimize for you. So something to consider. If you're working on graph problems, so if you're working with kind of large graph data structures or with graph algorithms, you might have a better experience using GraphX in the Apache Spark ecosystem than you would with the kind of equivalent projects in Dask. That's just, this is a line that I took straight from the Dask documentation. Actually, much of this material is directly from the Dask documentation. You can see links to it in the speaker notes for these slides. And to be honest, I've never worked with the kind of graph processing stuff in Dask, so I'm just taking the Dask documentation's word for that, but this might be a reason that you prefer Apache Spark. And then finally, if your main code base is in Java or Scala or R and not Python, you probably want to use Apache Spark. Dask is very, very focused on the Python ecosystem. I'm not telling you that it's impossible to use Dask with other languages. There's all kinds of like weird stuff you can do with libraries in one language that pass data and commands back and forth to, like a runtime in another language. There's stuff you can theoretically do, but if you have a large R code base that's been working on individual machines, and now you're looking to parallelize some of the data processing steps there, and everyone on your team writes R, Dask is probably not the right option for you, and you might have a better time with Spark. Something to consider. All right, that is all that I want to say about Dask versus Spark. This is a very big topic. We could go on forever talking about this. And to be honest, there are people who are much more qualified than me to give you a very, very, very deep dive into this topic. So most of what I just presented on the comparisons between these two things came directly from this document in the Dask documentation. You can go there to learn some more. And yeah, hopefully that will kind of satisfy your appetite for Spark versus Dask stuff, because that is the extent of that kind of stuff that we're going to cover in this talk. All right, now that we've gone over why you might use Dask for machine learning, why it might be interesting, next I'd like to talk about what Dask actually is. Let's go deep into the details of exactly how Dask works. I want to make one point really clear before we start this. Dask does work very well on a single machine. In fact, the first time that I used Dask, I didn't even know that Dask had any distributed computing, like multi-machine, any of that stuff. I thought that Dask was just a work with a data frame that's bigger than memory on one machine type of library, like big memory or big matrix in R, projects like that. So honestly, Dask is great on a single machine. However, for the purpose of this talk, from this point forward, I'm only going to talk about using Dask to orchestrate work over multiple machines. So I don't want you to walk away from this talk thinking, oh, I shouldn't care about Dask because I'm never going to do multiple machine stuff. Dask is great for single machine, but we're not going to talk about that anymore in this talk. All right. Next, I want to explain that Dask is not a library. So kind of capital D Dask is an ecosystem of many libraries. Lowercase d Dask is itself a library. You can pip install Dask. But Dask, from this point forward, when I say Dask, I'm going to mean the ecosystem. Dask, the ecosystem, contains many libraries for doing kind of different pieces of work. And so you'll see this notation with the brackets in some of the slide titles here. And in that, I'm referring to one of these projects, mostly taken from github.com/Dask. So you can go there and check out kind of what projects exist in the ecosystem. All right, so let's talk about how Dask kind of connects together multiple machines. So one of the common ways to do this is with a project in Dask called Distributed. And in Distributed, you have this nice separation of three infrastructure components: the client, the scheduler, and the worker. This graphic that you see on the right is not technically from the Dask documentation. This was posted by a Dask maintainer on a Dask issue about proposed updates to documentation. As of when I recorded this talk, that issue was still only a proposal, but I really, really like this. I think it's an accurate and very clear description of the infrastructure. And when you go access the slides later, you can look in the slide notes for a link to exactly where this image came from. Okay, so in Dask, there are these three kind of key components in distributed world. Let's talk first about the client. The client is just like your code in a notebook or your code, in a Python REPL on your laptop or whatever. This is the place where your code, your application logic, your thing that says, here's where my data is, I want to add these columns, I want to train this sweep model, whatever. Your code talks to a client, and then that is the only interaction that your code has with Dask in most kind of data processing and machine learning workflows. So your code might be using some of the Dask libraries, but your code is not going to be littered with like the IP addresses of workers or ports to communicate with them, or like any kind of stuff like that. Your code talks to a client, and then your client talks to something called the Dask scheduler. So every Dask distributed cluster has something called a scheduler, and the scheduler is going to be the thing that looks at the available workers. It looks at their available resources. It looks at what else they're working on. And then the scheduler is going to take a description of the work that you'd like Dask to do, and it's going to make sure that that work is divided up between the workers. And the scheduler will report back to the client stuff like the statuses of that work, or maybe logs from that work, maybe some data if you ask it to, stuff like that. And then finally, we have this thing called the worker. And so the workers, in most applications, the workers and your client are never going to talk directly to each other. It's possible, but it's not really like a standard pattern. The workers, their entire world, they just know about the scheduler, and through the scheduler, they can know about each other. And so the workers, they sit there, they are running a Dask worker process, and the scheduler sends them work to do. The scheduler says, all right, I need you to do this work. Here's the other data for it. Good luck. Let me know how it goes. And so you have this nice separation of client, scheduler, and worker. You'll see as we go through the rest of this talk that some of the different deployment options for Dask just involve basically plugging in a different scheduler and set of workers. And you'll see as we go through the talk that this kind of separation of these three components means that you can do that. You can say, this was running on my laptop, now it's running on Kubernetes, without making large changes to the rest of your code base, which is really cool. Okay, so next let's talk a little bit more about the scheduler and the workers. So I want to make something clear. In some frameworks, in some descriptions of parallel computing or distributed computing, the phrase worker will refer to a physical host. It'll refer to a physical machine. That can be true in Dask world, but it does not have to be true in Dask world. So the worker and the scheduler, these are just basically Python processes. If you pip install Dask, pip install distributed right now, you can run Dask-scheduler on your laptop. You could run Dask-worker in 3 different shells, and you'll have a little 3 worker distributed cluster right there on your laptop. So just keep that in mind as you think about some of this Dask stuff, as you read documentation for how to do things in Dask. The term worker in Dask world refers to a process and doesn't have to mean a physical machine. All right, so I want you to look at this picture again. Just keep this in mind, right? Client, scheduler, worker. This is going to be really important as we talk through this next piece. There are many options for running a Dask cluster on different types of infrastructure. There are many, many options. So for example, if you're already using Spark and you're already using Yarn as your kind of thing that knows about where all the worker machines are and how many resources they have, you can use the Dask Yarn project to run a Dask cluster on that same infrastructure. And so this could be like a Spark cluster that you run yourself, or it can be a Spark cluster maybe from Google Cloud's Dataproc or from EMR, or any of the other kind of hosted Spark things. So this is an option. If you're working in high performance computing and you already have an HPC cluster, and maybe you are running code as MPI applications or something like that, you could use the Dask job queue or Dask MPI projects to run a Dask cluster on that HPC cluster. Pretty cool, right? If you are working in Kubernetes, there is a Dask Helm chart so that you can basically just like Helm install Dask in Kubernetes, and that will spin up all of the different kind of components that you need to work with Dask in Kubernetes. You can also use the Dask Kubernetes library, which will basically give you these classes in Python that allow you to create schedulers and workers, which are each effectively Kubernetes pods. You can kind of think of it as like maybe each worker is a pod, the scheduler is a pod, and Dask Kubernetes will take care of some of those details like making sure that the pods can all kind of communicate with each other, that they have appropriate health checks, that kind of are knowledgeable about what it means for a Dask worker to be healthy, all that kind of like Kubernetes-y stuff you can do with Dask Kubernetes. If you want to run Dask on the public cloud and you don't want to, you totally can just get a bunch of virtual machines and run these CLI commands that I showed you. Like you can totally just do it yourself if you want 100% total fine-grained control over which machines are joining, what ports they use, et cetera, like you can do that. But there are also some options to take advantage of managed services from public cloud providers. So you can use Dask Kubernetes together with the managed Kubernetes offerings from Amazon, from Azure, from Google, et cetera. There are also kind of like maybe a half dozen or so other public cloud services that don't use Kubernetes, but that do some form of container orchestration. And you can use this really cool project called Dask Cloud Provider to run a Dask cluster using some of those services. So near the end of this demo, I'm going to actually show you an example of running a Dask cluster on AWS Fargate, which is a container orchestration service from Amazon that is not Kubernetes. It's kind of like, you can think of it as like you run a bunch of virtual machines and they each have a Docker daemon on them. And then this service like schedules containers onto one of the virtual machines, basically. So there are a lot of different ways to run Dask, and all of them involve basically this scheduler and these workers being run by kind of some other type of infrastructure. All right. So now that we've talked a little bit about deployment, let's talk through what happens when you ask Dask to do work. Excuse me. So all of the work in Dask is going to be arranged in a graph. So this image on the right from the Dask documentation gives you a very simple example of this. Notice two things. One is that each of the arrows here have a single kind of, they have a direction, right? The graphs that you built in Dask will be directed. There will be a sense of which tasks are dependencies of other tasks. And then notice these square boxes that are kind of sitting between different tasks, right? In Dask, individual tasks can have data dependencies on each other. And so all that means basically is you're not writing code that says, run this function, then run this function. Exactly. You might find yourself writing code that's like, run this function and then feed the output of that function as the input to this other function. And so you can have these kind of data dependencies where Dask is able to, look at those data dependencies and maybe do some optimizations around minimizing the movement of data between different workers or take advantage of caching to avoid recomputing things that already have been done, stuff like that. Okay, so when you write your Dask code, there are going to be 5 steps that happen in kind of turning your code into something that's actually a running application. The first step is construction of the Dask graph. So your code is going to be built into this ordered graph, and the graph is basically a dictionary of Python functions and their arguments. And the nesting within that dictionary gives you some information about the dependencies of the different functions. So just think of it as a dictionary full of Python functions. That's like the easiest way, I think, to visualize this. After the graph has been constructed, then Dask will enter a stage called optimization. So I think I mentioned this when we were talking about the difference between Spark and Dask. So Dask, will do some optimization where it will look at the work that you've described, and it'll do a little bit of stuff to try to maybe make that run faster or use less memory or something like that. So this is a stage where basically stuff is just being moved around in that dictionary. Maybe some unnecessary steps will be removed. Maybe some things will be kind of, just moved around, whatever it may be. Once Dask is pretty happy with the state of the graph and it says, I can't optimize this anymore, next you enter a stage called serialization. In serialization, the client takes that graph and basically puts it on the wire and sends it out to the scheduler, who then sends it to the workers. And so at this point, there's no more optimization happening, like the work that's been done has been described and the scheduler and the workers, they know about it. Once the scheduler and the workers know about the work to be done, then you'll enter a phase called scheduling. And so in scheduling, the scheduler looks at the graph, it looks at which pieces have been done yet. At the beginning, none of them, right? And it looks at the workers, it checks which workers are healthy, how many do I have, how much memory do they have, stuff like that. And then the scheduler will send work to those workers. And when it sends work to those workers, it will send them individual tasks. And then it'll expect the workers to report back things like logs, task statuses, the location of data, stuff like that. And then finally, you enter this phase called execution. In execution, workers receive a message from the scheduler that says, hey, run this task. And they say, okay, I'm going to run it. And then they run your code. They run your code. They use, the available local memory. They use the available CPUs. They might write to disk. And they'll send back to the scheduler information like whether or not they completed a task. They'll forward back logs from running the task. They will, if they create some output and they store it in distributed memory, they might describe to the scheduler how to reference that memory so that if other workers need that data for something, the scheduler knows how to kind of instruct the workers to move that data around, stuff like that. But then, of course, as this goes, it's not like you submit a single graph and then you just kind of like wait for it to be done and then you do more work. You can constantly be asking the cluster to do more work. And even workers can themselves add additional tasks to be done. They can like generate their own kind of tasks to be scheduled if they want. So this process is circular. It will just like run and run and run. until all of your stuff is done. But that's kind of the basic idea of what's going to happen. All right, so if you want to create your own custom Dask graphs, you can use a component called Dask delayed. This image in this code sample is taken directly from the Dask documentation. And so let's talk through what is happening here. What I've omitted here, just for the sake of not making the slide too crowded, is the definition of three functions. Inc takes in a number and increments it. It adds 1. Double takes in a number and returns that number multiplied by 2. And add takes in 2 numbers and returns their sum. So these are 3 kind of functions that I have defined in the global environment. By wrapping those functions in this call dask.delayed, I'm basically saying I'd like to create a future that refers to the eventual result of calling, say, the double function on an input x. But I don't actually want to do that work yet. I just want to describe what it would be like to do that work. Remember that I said that the Dask graph is a dictionary of function calls, basically, right? Those function calls, they're futures like this. They kind of describe the input data and the code to run over that data, but they aren't run quite yet. And so when you do this, when you keep wrapping code in these dask.delayed calls, this is one way to build up a custom graph. And so look at, for example, add. You can see that add takes in the result of calling inc, that's A, and the result of calling double, that's B. And we have add AB, right? That exactly shows up in dependencies over here on the right in the graph. So you can see, like, if you look in the bottom left corner of this graph, right? We have inc and double both being called. They each produce 1 output. Their outputs must both be given to 1 call of add, and then add produces itself 1 output, and sum takes each of those add outputs, sums them together, and gives you a single number. And so this is, in this way, this is kind of a simple example meant to demonstrate the point, but hopefully you can see that you could create very, very complicated stuff very quickly if you want. And then you can rely on Dask to handle the orchestration of, which things rely on other things, which intermediate outputs can be evicted from memory because they're no longer needed. So for example, once add is complete here and it produces the value in this box, the values from inc and double, they can then be thrown away because no other tasks rely on them, stuff like that. But this is kind of what you can do if you want to build up your own Dask task graph totally from scratch. Okay, well, we're data scientists, right? We're not all computer scientists, algorithms, researchers. That might be a little bit much for some of us. And so the next kind of level up from creating your own graph like that is using the distributed data structures available in Dask. I mentioned these earlier, but there are 3 of them. The Dask bag is kind of like a list in Python, basically, or it's like an RDD in Spark. And this supports those functional programming fundamentals like map, filter, or reduce. The Dask array looks and feels like a NumPy array, and it follows the same API. So this is, these are basically arrays. They can have all of the different kind of the same data types that NumPy supports. And then finally, you have data frames. And in data frames, the Dask data frame will follow the same API as Pandas data frame. And yeah, I think that's enough to say about that, to be honest. So I mentioned a couple slides ago that I found this really, really good graphic deep in a Dask issue, not yet merged into the Dask documentation, right? Well, this image is from the same issue. I really, really like it, and I think that it really describes the concept of the Dask array very clearly. And so let's talk through that so we can kind of all have a shared understanding of how this is working. So first, consider this NumPy array on the left, right? We have a 6-element array here. And when you call .sum on that array, what's going to happen? Well, the code in that library is going to go, okay, take this first number, add the second number, then add the third, then add the fourth, et cetera, and give you back a sum, right? Just six pieces of data, add it together, you get back the sum. In the equivalent Dask array, to your code, the array looks exactly the same. You have your Dask array in memory, you call .sum, and you get back a single number that is the sum of all the elements in the array. However, what happens kind of under the hood is that Dask is going to take your .sum call and it's going to generate a small Dask task graph like you saw before. So this single array might actually be broken into two physical pieces. Here in this image, they're called chunk 0 and chunk 1. These two physical pieces might be on different machines. It doesn't really matter to Dask. I mean, Dask will figure it out for you. And what Dask is going to do is it's going to generate a task graph that says, okay, for each chunk, call .sum on that chunk, then collect together all of the chunk sums, sum those, and then I'm going to be able to give you kind of the global sum of the whole array. This is how all of the operations on the Dask collections work. You write code that looks and feels like the equivalent kind of local non-Dask version of an operation, or chain together very complicated pipelines of operations. And then Dask will turn those into a task graph, which is then given to the scheduler to then give to the workers to execute and return data for you. So this is kind of the next level up of in terms of kind of high level APIs for creating Dask task graphs, basically. If we go even another level up, or honestly maybe like 2 or 3 more levels up in kind of generality, you have machine learning libraries like DaskML, like the LightGBM integration for Dask, the XGBoost integration for Dask. In these, they expect the input data to be in these Dask collections, like Dask data frame or Dask array, and then they will perform distributed training on that data and return to you a model object. And so in DaskML, you're going to find some things that look identical to scikit-learn, like the metrics functions. There's a grid search CV, things like that. And then there are also some like really interesting things specific to DaskML for maybe ensembling together the results of multiple distributed fits of some different models. It's all kinds of cool stuff there. In XGBoost and LightGBM, you're going to find code that looks and feels extremely similar to the XGBoost and LightGBM Python packages without Dask. So if you look at this code sample on the right, this is a code sample taken from the LightGBM Dask integration. That integration is still being actively developed, but as of a few weeks ago, this is kind of what it looked like. And hopefully, if you've used scikit-learn before, if you've used maybe XGBoost or LightGBM even, hopefully you should look at this and say, wow, that looks extremely similar to the non-Dask code that I've been writing. And that's exactly the plan. So you set up a little bit of data. Here I'm using a Dask array. You set up your estimator. These parameters, there's nothing Dask specific about them at all. They're just like standard gradient boosting, stuff, whatever. And then you call .fit and you get back a model. At this point, it's important that I share a little bit of history with you about using XGBoost and LightGBM on Dask. So if you walk away from this talk today thinking, whoa, I really, really, really want to go use Dask for machine learning, and I really like XGBoost, or I really like LightGBM, and you go Google and you look around on Stack Overflow for like, how do I use Dask with LightGBM? You might stumble onto these projects, one called Dask XGBoost and one called Dask LightGBM. These projects, as of this moment, should be considered deprecated. So what happened here, I can kind of briefly give you the history. What happened here is when XGBoost and LightGBM, when these projects were first created, soon after their creation, they took on distributed training interfaces. Both XGBoost and LightGBM have their own distributed training interfaces written in C++. After some period of time, as Dask became popular, as people started to do machine learning work in Dask, the lack of a Dask interface for, basically taking advantage of Dask data frames for data processing, but then using distributed XGBoost or distributed LightGBM for training, the lack of that interface led some volunteers in the Dask community to create these libraries, Dask XGBoost and Dask LightGBM. So these were not created by maintainers of XGBoost and LightGBM, but by people who were just passionate about doing machine learning in Dask and who volunteered their time to figure out basically how to describe to Dask distributed gradient boosted decision tree training. In September 2019, Dask XGBoost was formally merged into XGBoost. It was upstreamed into XGBoost. And so what that means is that since then, there has been an XGBoost native Dask integration. If you just pip install XGBoost, you can just use Dask and it's going to be great. In LightGBM, we were about a year, that's generous, maybe like a year and a half behind XGBoost on taking that on. But similarly, the maintainers of Dask LightGBM agreed to merge Dask LightGBM into LightGBM. And so in the 3.2.0 release of LightGBM, if you install that release, you can just, import lightgbm.dask, and you'll be able to use a Dask interface to LightGBM that is maintained by the LightGBM maintainers, that is tested on every build, on every commit with other changes to LightGBM, and that whose API will evolve as the rest of LightGBM evolves. So I know that was a little long-winded. I really want to be sure that I make this point. Do not write any new code using Dask-XGBoost or Dask-LightGBM. Okay, and with that, next I'd like to move on to a live demo. I'm just going to pause for one moment and take a sip of water. Okay, let's go to a demo. So the setup for this demo requires a little bit of work in Docker. It's using all open source technologies, things that you can get for free, but it does take a little bit of time. So I've kind of, how when you watch a cooking show, they say okay, put all the stuff on the turkey and then cook it for 8 hours. And they come back from commercial, it's the turkey's done. I've kind of done that here. I've kind of already set up some of the details for us to work with. But all of the materials that you're going to see demoed are available in this public repository, github.com/jameslam/lightgbm Dask testing. This is the project that I use to test LightGBM on different types of Dask clusters that are not very easy, I shouldn't even say easy, that are not really cost effective for us to set up in LightGBM's continuous integration. So you can find all of the code here, all of the setup. This is released with a permissive open source project, so you can just take it and make it your own if you'd like. Pull requests are welcome, but I'll be using some of the setup from here. So as part of that setup, I have already cloned LightGBM, and I've generated 2 Docker images, and I'll just show you kind of what's going on in these Docker images. The first is built in 2 steps. It comes from the Dask Docker project. So Dask/Dask Docker comes from the Dask Docker project, which is just basically a set of Docker files that are used to build images pushed to Docker Hub for doing Dask stuff. And this particular Docker image comes from the Dask notebook image, which already has all the cool stuff to run Jupyter. And I'm just pip installing, conda installing some other typical stuff, scikit-learn, AWS CLI, pandas, etc. So that's what I'm going to be using. Oh, and sorry. And then so that builds a first image. And then when you build a second image, all that I'm doing is at build time, copying in LightGBM and building it from source. And so I've already built these images. And then there's one more image that we'll get to near the end of the tutorial, which does not have any of the notebook dependencies, but it's instead intended to be kind of a deployment image, an image that you might use, say, on AWS. And that's exactly what we're going to do. But you should see, again, all I'm basically doing is conda installing and pip installing some stuff, and then installing LightGBM from source, and then cleaning up. So nothing too bad here. All right, so I have actually already built those images. And so from the root of this repo, here I am, LightGBM Dask testing. I'm going to start up the notebook, and I offer a make file in this project so that you don't have to memorize a bunch of super long commands. So I'm going to run make start notebook. So if you have already cloned the repo and you've already kind of followed the prep steps from before this talk, then you should be able to do this. I recommend that you open 2 terminal windows right away when you start, and that both of them be at the root of this repository. So you're not going to be able to kind of Control C interrupt this notebook once it starts running. All right, so that should just take a second to spin up. And then what you can see here is I'm also mounting in some AWS credentials. This is absolutely not required at all. I'm going to show you two examples. One of those examples does not rely on AWS. One's just going to run on my laptop. The other does require AWS. But it is absolutely not required at all that you that you mount in your AWS credentials. Okay, now that this is running, we can take a look. And we can go into the notebook. Okay, so once you come into the notebook, you're going to open up this demo.ipynb. This contains a demo running on local cluster. So the local cluster is an implementation of that Dask distributed cluster that basically just works on one machine. So in this case, it's on my laptop. And this is going to be a little 3-worker Dask cluster running inside of a Docker container that I'm running on my laptop. So let's take a look. Should just take a second or two to spin up. All right, great. So at this point, I've said I want 3 worker processes. I've created a distributed client attached to this cluster. And then I ran this command wait for workers to say basically block this cell until all 3 workers come up. If I didn't do this, this cell would return earlier. And then we would just be kind of like awkwardly waiting for all the workers to come up. So in this case, they all come up. And for every Dask distributed cluster, you'll be able to view something called the Dask Diagnostic Dashboard. And so that's always going to be accessible at cluster.dashboard link. So let's take a look at that. This diagnostic dashboard, it's a bokeh app basically. It's going to show you some information. Doesn't look that interesting right now because I'm not doing anything on the cluster. But you have a couple of things you can use for monitoring. So this kind of home status page, this will show you like what work is being done on the cluster right now, and you'll see that in a second. The workers tab will show you how many workers have joined the cluster, what are their IP addresses. So in this case, they're all on my machine, so they're all on the same IP with three different randomly chosen ports. How many threads have the workers been given? What kind of CPU utilization are they at right now? How much memory are they using up? Stuff like that. You can use the tasks graph to see kind of a larger view of the task stream. And if you have like a fairly complicated task graph that's executing, you'll be able to use this view to see kind of what's going on in the cluster. You can use the system tab to see what's going on in the scheduler. So this will give you some diagnostic information about the scheduler. There are some cases in Dask where if you aren't careful, you'll be asking the scheduler to do a lot more work than you may be comfortable with. For example, passing a ton of data from the client through to the workers or something like that. So this can be useful for checking that. Dask does come in with a built-in profiler. So as we run some more code, this will get more interesting, but Dask will give you some information about which parts of your code tend to take a lot of time or tend to be used a lot, which can be interesting. When we run something, you'll see the Dask task graph here. And then finally, info is just kind of a separate little bit of information where you can go all the way down into each worker's logs and just kind of see what's going on. All right, so we have our Dask dashboard set up. Let's go do some stuff. So next, we're going to get some data and put it into one of those Dask collections. In this case, I'm going to use a Dask array. And what I'm going to do is load up a NumPy array using one of the scikit-learn datasets functions, and then basically send that out to the cluster. I want to make it really clear before I do that. That is not the only way to generate a Dask data frame or a Dask array. In fact, many times you're probably not going to want to do that. But I wanted to make this tutorial kind of an approachable first step from pandas and scikit-learn towards Dask. So This is totally a valid option. Like it's totally a thing you can do. Say, take this data that I have locally, send it out to the cluster. But Dask does also have a ton of options for you to basically send work to each cluster, each worker, where each worker says, I'm going to, read in a batch of files from an object store, or I'm going to run some functions that query a database or something, and have each worker basically read in its own partition of the data without that data ever having to all live on the client or all get shuffled around the cluster. So I just want to make that really clear. All right, now that I've hedged against that, let's do this. Let's go see what's happening in our dashboard. Okay, it ran extremely fast, so we didn't really get to see anything. But what happened here is I've basically, that's right. I know why this ran fast. Every time I do this demo, I make the same mistake. That ran extremely fast and nothing happened because of this property that we talked about when we were talking about delayed functions. At this moment, if we look at, say, dx, this dx isn't, there's no data in there yet. It's not really a 10,000 row array. It's just like a promise of an array. And if we print it, you'll see this little thing. This is not what you expect to see when you print an array, right? You expect to see like the first 10 or 100 records or something. This is just the information that Dask has right now. And all Dask knows right now is this is going to be an array. It's going to have this shape. It's going to take 10 separate function calls to totally materialize the array. But we haven't actually asked Dask to do anything yet. So if I look on the workers, each worker has about 55 megabytes of stuff in memory, right? So just remember this, we're around 8.4% memory utilization. Dask is not going to actually materialize that data, basically run all of those function calls until I ask for that. And so what I'm going to do right now is something that's totally optional in machine learning with Dask, and that is to persist the data. And so by persisting, what I'm going to tell Dask is to do two things. I'm going to say run all of those function calls to materialize the data and cache it permanently in memory. Until I explicitly tell you to delete it, don't delete it just because other tasks aren't using it. So let's do that. Take a look. Okay, I intentionally chose a fairly small amount of data here, but hopefully you can see our memory utilization went from like 8 point something to 9 point something. And a little bit of work was done. It was extremely quick. And you can see what kind of happened here. We ended up getting 20 of these tasks that generate an array. Okay. Great. So we have our data set. Now it's like all set up. It's ready to go. We can do stuff like I talked about before. We can grab the sum of an array or something. Like you can see there's some operations here. So let's talk about what happened here actually when I ran sum. This is really similar to the Dask array example that I gave before during the talk. Right, so what happened here is a task called transfer sum partial ran. That you can think of as like each worker computing the sum of kind of its chunks of the data. And then deserialize sum partial, that's like put this sum on the wire and then send it to one process that adds them all back up together with this aggregate task and gave us back kind of the sum of this array, just as a small example. All right, enough. I know you don't care about taking the sum of an array, totally fine. Let's train a machine learning model. Here I'm going to use lightgbm.dask. I just, I have an affinity for lightgbm. I'm a lightgbm contributor, maintainer, and so I am going to import the Dask LGBM regressor class from lightgbm.dask. This is going to be used to train a regression model. We have a regression data set. I've set some lightgbm parameters here. They're not necessary. I just wanted to show that you can set them. And then I'm going to fit the model. And what you should see during training is, if we look at the graph, did that already finish? Let's use more. Let's use more iterations so that I can tell an interesting story. Let's do like 150 iterations. Okay. When we come look at the graph, you're going to see these three tasks. So you're going to see one of these train part tasks per Dask worker. The way that lightgbm distributed training works, all of the individual pieces of data on each worker get merged together into one local data set. So then we'll be left with kind of, you can think of it as like 3 matrices, 1 per worker, without any data being shuffled between workers. And then on each worker runs a long-running training process, which is basically bootstrapping a regular LightGBM network. So remember that I said before that LightGBM kind of has its own implementation of distributed training, right? What I'm doing here is I'm using a Dask task on each worker that is basically acting like a long-lived LightGBM worker. And then at the end of the process, we're going to get back this Dask LGBM regressor object. And if we want to look around in this object, this is going to look exactly like, say, the scikit-learn, LightGBM scikit-learn API, like the models that come from that. So we can see, you know, is it fitted? Of course, not on the class, on the instance. Is it fitted? We can see that it has a LightGBM booster in it. That booster is a regular LightGBM booster, so we can do stuff like get a data frame of the tree structure and see which features were used in each tree. You can go as deep with this as you want. We can grab all of the parameters. If you want to see the full set of parameters that were used during training, all kinds of cool stuff. Okay, so now I have my model object. Next, I want to do some evaluation. Most of the libraries in the Dask machine learning ecosystem will allow you to do evaluation using Dask as well. Actually, let me stop here and start up our AWS example, and then we can get to it in a few minutes, because that will take a few minutes to run. And I promise I will explain what's going on in that code. All right, coming back here. So imagine if you have your model, you're ready to go, and maybe your evaluation data is also in a Dask collection. It's in a Dask array or a Dask data frame. This can totally happen, right? Like you're having evaluation data that's too large to fit on kind of your normal workstation. There's nothing unusual about that. That can totally happen. Well, LightGBM, XGBoost, DaskML, cuML, many of the different kind of machine learning with Dask projects will allow you to call the predict method from an estimator on data that are stored in a Dask array or Dask data frame. So in this case, I'm just going to predict on the training data, just like let's basically see the in-sample fit kind of this model. And the first thing you should see is this returns immediately and gives us back a Dask array. So just like we saw before, at this point, this is just kind of a lazy collection of function calls that have not been run yet. Okay, very cool, very cool. Before I calculate any metrics, I want to see how the target is distributed so that we have some understanding of whether or not my model is any good. Spoiler alert, it's not very good. But let's see just how bad it is. And so in this case, further up here, in case I went through this too quick, I imported dask.array as DA. So that's what DA is here. And I'm going to use da.percentile. This is just like, np.percentile that you should be used to. And then I'm going to call .compute. Calling .compute on any Dask collection or any kind of list of Dask futures or whatever says basically, okay, Dask, execute all my code and give me back the answer. And pretty quickly, you should be able to see these tasks are they ran so quick. The width of the bars here is the runtime. They ran so quick that I can't even hover over this, but trust me that these are percentile calls. Okay, take a look at this for 1 second while I plug in my laptop. You can see that I'm losing battery here. Okay, we are charged up and ready to continue. So you can see that this variable is distributed, roughly in the range between negative 630 and call it negative 420, something like that. So what I'd like to do is evaluate the mean absolute error of my model, and I'm going to use the mean absolute error function from DaskML metrics. So these metrics functions in DaskML, they're intended to look extremely similar to the metrics that are available from the scikit-learn metrics submodule. And if I run that, let's see what we get. So both of these inputs, notice that both of these inputs are Dask arrays. And I get a mean absolute error of 17 for something where the 25th and the 75th percentile are separated by, call it 60. I'm not like thrilled with an MAE of 17, but it's something. It just at least shows you that the LightGBM model isn't like a random number generator. Or maybe it doesn't show that and you just kind of have to believe me. But so this is the general machine learning on Dask workflow. Let's just see how this is going. Beautiful. So this is going to be your general machine learning on Dask workflow. Finally, I just want to make one more point about that. Having Dask as a training time dependency, a library that has to be there when you train models, do hyperparameter tuning, doesn't mean that you have to take on a Dask as a dependency for when the model is deployed. So I actually really like the pattern of using Dask for your kind of large-scale data loading, feature engineering, model tuning, model training, but then extracting a non-Dask model object out of the Dask model object and using that non-Dask model object in a deployment so that your scoring environment is a lot lighter weight. It's a lot. It has fewer dependencies. It's kind of easier to work in. In LightGBM and XGBoost, you can do that in a few ways. One that I think should be the most familiar and maybe the most accessible to the audience here is taking the Dask model object and extracting from it a scikit-learn equivalent. So here I've taken my model object. Remember, this was like a Dask LGBM regressor. And I'm going to take out of there a different model object using the method toLocal. And that's going to be a LightGBM sklearn LGBM regressor. And I'll prove that to you like this. There you go. And so that thing you'll be able to kind of store with something like CloudPickle and unpickle it later. But most importantly, you'll be able to unpickle it later without needing to have Dask as a dependency. It has no reliance on Dask. The model object has no more Dask stuff in it. And so you might find that valuable as a deployment option. Okay, that's the extent of the demo that I wanted to show on local cluster. You can learn more about this in the in the documentation for LightGBM. If you do try the LightGBM example, please come open an issue. We are looking for people to come help and contribute with some of this stuff. Okay, that's the extent of local cluster. I want to show you briefly an example on AWS. This notebook should look extremely similar to you. So in the first cell of this notebook, I'm loading in a little bit of kind of implementation-specific stuff from this LightGBM Dask testing project that I set up. What's basically happening here is that I have pushed a Docker image to Amazon's Elastic Container Registry, the public version of it, and then when I get back the result from Amazon of like where to find that image and what the tag is, I write that to a little JSON. I'm just reading that into a cell here. And then I'm going to use that to tell Dask Cloud Provider what Docker image to use when spinning up my Dask cluster. So I've imported Dask Cloud Provider, and then running this Fargate cluster code is going to create a cluster of 3 workers and 1 scheduler, which are each tasks out on an AWS Fargate cluster. And you should notice this code, cluster, client, wait for workers, looks very similar to the it just works on my laptop example. After I've done that, just like before, we can get a dashboard link, except this time, if you look at the workers, these 3 IP addresses are different. These workers are 3 EC2 instances in AWS. It's Pretty cool, right? Okay. And then from that point, training looks exactly the same. Everything is a little bit slower because there's a little bit of extra communication overhead going from my laptop to AWS and back. Let's do this with another 100 iterations. But you should see training is going to look exactly the same. We're going to have these 3 long-lived kind of train part tasks. All of this is running on AWS. None of this is running on my laptop. Right now it's looking for ports for workers. Sounds good. Just doing stuff. We could go look at the workers' logs. You should be able to see a little bit of information about what they're doing. And okay, and then our training is done. And what you should see is all the rest of this works exactly the same way. Same distribution of the data, same metrics. I trained for fewer iterations here, so the MAE is a little bit worse. I know that I went through that one a lot faster. What I really want you to take away is that in this notebook, I trained on my laptop. In this notebook, I trained on AWS with the same data set, the same logic, the same everything. The only thing that I had to change to switch from my laptop to AWS was this block right here, where I say, hey, I'm going to use a different type of cluster. I'm going to set up a client for it. And from that point forward, nothing else in my code needed to care that I was on my laptop or AWS or DigitalOcean or whatever. So that is really the power of those Dask abstractions of client, scheduler, and worker. And I encourage you to try these examples on your own. Okay. So yeah, as I mentioned, I encourage you to try these examples on your own. If you go to this link, and this link should be available in the talk information as well, here you'll find recordings of past versions of this talk. You'll find the slides from this talk, and you'll find a link back to that LightGBM Dask testing repo that I showed earlier that contains all of the kind of demo and setup code. Finally, before I go, I'd like to make a pitch. If you are interested in making open source contributions, if you're interested in Dask, if you're interested in LightGBM, we really, really would appreciate your help. I really encourage you, come into LightGBM, look at our open issues, look at this particular issue where we track feature requests. The Dask interface in LightGBM is very new, and because it's very new, there is a lot of opportunity for improvement for contribution. So if you're interested, we really, really would appreciate your help and your support. And with that, thank you so much for your time. Thank you to ODSC for having me. You can contact me at any of these places, and enjoy the rest of the conference.